All right, let's get started. I'm already running late. All right, so let's take attendance real quick. If you come in late to class, okay, if you've come in late to class in the past and you didn't do this, you've been counted absent. So you need to make sure that we get that squared away. If you came in 5 or 10 minutes late and you didn't do it, I've got you marked as absent. So we'll just make sure you were here. All right. Everyone good? All right. Now, the next thing I'd like to know is if you feel like you are ready for a quiz today. Let me know yes or no. All right. You're not getting a quiz today. All right. So I was hoping more people would say yes, but it's because we have a lot to do. All right. We have a lot to cover, and so we don't really have a lot of time for a quiz today. Hey, come on in. It's all right. I wasn't saying yes or no, do you want a quiz? I said, are you ready for a quiz? Okay, so everyone has the handout? All right, I did hear someone mention we have a test coming up. Our first exam isn't until the 19th of February, so we still got a ways to go here. It's a Thursday. Well, that's when it's scheduled. We'll see when we get there if that's what happens. No. 2 weeks from now? Something like that. Yeah, 2 weeks from this Thursday. Yep. Okay, so I had a question over homework. Yes? What was that one that was that a homework problem? Who asked me about it? 59. Yes? Number 59? You didn't have to do 59? Ah, okay. That's why. I sent an email saying which ones to do and which ones not to do. So that one we didn't do. So let me lecture today, and after we lecture, maybe you'll be able to go back and do it. 7 through what? 47 through 56 is all I wanted you to do.
I don't understand.
I know it's 47 and 56.
57?
Okay, so again, let's wait on that, because today's material will help you with that, okay?
Oh, 47 through
All right, so everyone have the notes? Yes? You picked those up over there? All right, so I'm starting to get some pretty good notes together, but the issue I'm having is that sometimes I have typos, and I have some typos in the 3-3 notes, but I had already printed them. So I'll have you correct them as I get to them, all right? We are going to pick up with 31.7. Or is it 318? The examples, right? Okay. So what we had not done yet in last class, we were doing domains, right? And we had not done D? I thought we did do D. We did not do E. So we did D? That's what I thought. I looked at my notes. I want to pick up here at E today. So for E, this is a very interesting problem. We have h of z is z plus 1 over z plus 1. And we're being asked for the domain. Now this function, the name of the function is h. The independent variable is what? What's the independent variable? The one that gets plugged in, z, right? Okay, so we want to know what values of z you can or cannot plug into this function. Now when we were looking at the notes, there's something in bold at the very bottom. Right here it said, oh, important note, always check for domain issues prior to algebraic simplification, right? So when we're looking at this, I believe everyone in here would agree that we've been taught that anything divided by itself is 1. Yes? So we all want to say, hey, look, this is equal to 1. But when we do that, we have to guarantee ourselves that this denominator was never 0. So there's one value of z that we still cannot plug in, and that's what? Z cannot be -1. Now, the way we do that is we took the denominator, we set up the equation, we said, hey, when is that 0? We figured out that that's when z is -1, and we want to throw that out of our domain. So our domain would be all the whats? Everything except -1. So all x's, all z's. I'm using the set notation. All z's such that everything except z. I can just say z is not equal to -1. That's the domain.
If z is -1, then the top would also be -1, and it would be 0.
That's the key of why I'm giving you this problem. You have to look at domain before the algebra. That's the way functions work. I've defined this function this way, and by me defining this function this way, why didn't I just say 1? Why didn't I just give you the function 1? Right? If I come in here and say, hey, I have a new function, I'm called g of z, and it's equal to just 1. That function has no domain issues, because you can plug everything in. The answer is 1. But if I define a function that way, I'm telling you it's 1, except for there's one place you're not allowed to plug in, and that's at z is -1. You cannot divide 0 by 0. That's right. It's undefined. Yep. Interval notation, yes. -infinity to -1, parenthesis, union, -1 to infinity. So that would be on a number line, that's everything moving from left to right, everything, all negative numbers up to -1. Jump over -1 and then go from -1 to the right forever. Yes? What's wrong? Oh, you're pointing at the number line that I just imagined? Okay, all right. Okay. All right, so the key to this problem is that you must address domains before algebraic simplification. Yes?
Oh, okay, so with brackets, it means that it's long.
You want to include that.
To include that, and with parentheses, it's not.
Yeah, that bracket would mean I want to include -1, which I don't want to. So that's why I use the parenthesis. Okay, F. Here's what we're going to do. On F is a little bit beyond where I want to go, because we have an entire section coming up, specifically section 4.5, which is the last section before the test, which will address how to do this in a more precise manner. But I still think it's something that we can tackle here. All right? I guess what I'm trying to tell you is that I'm hoping things are going to get a little bit better for a problem like this later. But we'll see what we can do. All right, so we have a function, f of x is equal to the square root, all this, blah, blah, blah. So what is it that we have to worry about with square roots? You cannot have a negative under there, right? You could have 0, but you can have anything bigger than 0, but you cannot have negative. So the technique that we used was what? Someone tell me. What am I going to do? Set the whole thing, even the square root?
No.
You don't have to. Just the thing underneath. What do we call that thing underneath? The radicand. You take the radicand. This is what you do with all square roots, okay? You take the radicand, and you set up not an equation, but an inequality. The inequality is that we need this to be greater than or equal to 0. And this is what's called a quadratic inequality. I'm writing this down because you might want to go, YouTube some videos on quadratic inequalities, but remember, we're going to get to it in 4.5. The idea here is this. This thing right here, we need to guarantee it's going to be bigger than or equal to 0. the fact that it's a quadratic complicates things quite a bit. What we can say about quadratics is where they're equal to 0, right? That's what we're good at. We can set quadratics equal to 0 and solve those. So that's the way we always start a quadratic inequality, where you're going to first solve this. So notice I'm changing from the inequality to equality. And then how would you solve this quadratic here? You try and factor it, right? You could use quadratic formula. This one factors. Anybody want to volunteer the factoring of that? 2x, x, 4 plus 1 plus, does that work? 2x squared, 8x, 9x, and 4. So that's the correct factoring of that. And now you set each factor to 0. Could I what? I can't go through that. That's what I've been saying since day 1. You have to be able to factor in this class. It's a you have to be able to do this. You're asking me how I'm getting from here to here. And that's what you have to be able to do day 1 of this class. And I've been saying since day 1, you've got to get refreshed on that. If that's a problem, you got to go to the lab, come to me, something. I'm happy to help you, but I can't go through and teach everyone how to factor quadratics. That's not what this class is for. Okay? So please seek the help if that's the step you're stuck on. At this point, you set each one equal to 0. I hate to tell students, no, I'm not willing to talk about it, but really, we don't have time for it. It's a lot. To get good at that, it takes a long time. I can't do it in one class and all of a sudden you're an expert. Okay, setting each one equal to 0. Again, I'm not showing that work, but you're just setting up 2 linear equations and setting them to 0. You got your 2 answers. So what we know is this. If I have a number line, I'm saying that at negative 4 and negative 1/2, I know that that's where this thing up here, right, will be equal to 0. And that's okay, right? That's okay to have. I said it had to be greater than or equal to 0. So what I'm doing is I'm starting to draw my number line. I do want to include these points. I'm going to put them as solid dots. So I do want those, right? The question is, do you want the stuff? I'm going to kind of break this number line. Imagine the number line is being broken into 3 sections. We've got everything to the left of negative 4, everything between these two, and everything to the right. Right? The question is, do you include the stuff to the left of negative 4 or not? Do you include the stuff in here, yes or no? Do you include the stuff over here, yes or no? So how can we figure that out? There's several approaches to this. One approach is just looking at the quadratic itself. Now let's do a vote on your clickers right now. How many of you have seen basically the idea of quadratics when you graph them, that they look like these things called parabolas? Yes or no? Have y'all seen that? Okay. All right, I think that's enough of you who have. All quadratics look like U's, right? They either go up or they go down. How do you determine if they go up or down? How do you determine if it's an up parabola versus down? What do you look at? You look at what's called the leading coefficient. You look at the number in front of the x squared. If that is positive, it opens up, right? If it's negative, it opens down. And we're going to spend a whole section doing this in detail. But if enough of you are comfortable with that, that's the easiest way to do this, all right? So I'm going to go with the numbers over there on my survey, and we're going to say enough of you understand that, and we are going to come in here and now draw a parabola. See, this parabola, we know that it hits at 0 here and here, right? And if I draw it, there's only one way to draw it where it opens up. It would be do something like this, right? Do y'all see that? And what I want to know is, where is this thing bigger than 0? Bigger than 0 means positive. So where is your graph positive? Where is it above the x-axis? Is it above the x-axis over here? Yes, right? So I'm going to put a big check mark over here. Everything over here looks like it's good. How about between here and here? Is my red graph above the x-axis? No. So I don't want stuff in there. The red graph comes down below the x-axis, right? Like below. So those are all negative numbers down there. And then to the right, all the red is above, so those are all positive numbers. So I want those, don't I? So that means I want everything to the left of -4, everything to the right of -1/2. That make sense? Okay. So I'm going to just draw everything out that way and everything out that way. And then I'll write my answer in. I'll start with the interval notation, then we'll do set. I usually do set first, but I think interval is easier to do on this one. How do I say everything to the left of -4? -infinity all the way to -4, bracket or parenthesis? Bracket, okay? Because I want -4, don't I? And then union now, bracket, because I want what number? -1/2 all the way to infinity. That's your interval notation for that domain. Okay, so now in set notation, I would go everything, all the x's such that, well, I want my -4, sorry, I'll do it this way. I want my x's to be less than or equal to -4. And we said commas for ands. And x must be greater than or equal to -1/2. That's probably the easiest way to do it. This is just saying, look, all your values of x have to be smaller than -4 to the left of it, and all your x's could be bigger than -1/2 to the right. That would be okay. Yes, that would be okay. Yes. Yes. Visualize it. Yes. That's why drawing this picture is usually something that I look for on a test, is that you've drawn the picture that shows that you understand that you know what's going on here. Yes?
When you use that inequality, everything on the left needs to be bigger than 0.
Bigger than or equal to 0.
Yeah.
Yes. No problem. Okay, we're going to move on. So now we get into what's called the arithmetic operations on functions, or arithmetic. Okay, we all know that growing up, people, when you were learning numbers, right, you started off, they gave you numbers, you started adding them together, and then you subtracted them, right, multiplied them and divided them. But those were numbers. You take two numbers, you add them up, you get a number, right? Take two numbers, you multiply them, you get a number. Well, you can do the same thing with functions. If you start with two functions, you can add them and get a function. You can subtract them and get a new function. Multiply and get a new function. And we just need to be able to make sure we understand how to do that mechanically. So there are four operations. There is addition. So this is notation, all right? When you see an f plus g in parentheses, that's telling you you need to add the f function to the g function. So mechanically what we're going to do is take whatever f is, and then put a plus sign, and then write down whatever g is, and then add them together, collect like terms, do whatever algebra is necessary, put them together, all right? We don't want to overcomplicate this, all right? It's just, I give you two functions, you add them. Then if I subtract, here's the notation, here's what you do. What is it about subtraction you have to be careful with? The order of things, right? 4 minus 2 is not the same as 2 minus 4. So if we say f minus g, that is not the same as g minus f, is it? So just be careful with the order and be careful with this sign. Multiplication, you just write f next to g. You don't need a dot next in between them. The book uses a dot, but in calculus books, they don't use a dot. So fg means multiplication. And then, this is hard to see, but this is f over g, which, as you would think, would mean division. The only thing you have to worry about with division, of course, is that the g function can never be 0. If it's 0, then it's undefined. So as long as that g is not 0, then you're good to go. So I have some functions here that I want us to perform the 4 arithmetic operations on. So let's do these. Oh, I went way too far there. So for A, I'm going to work kind of quick through these. So let's first add them. So when you add things, all you do is, you write the two functions down. You add them, so put a plus sign between them. So question here was, would it help to put them in parentheses? With addition, you really don't get in trouble too much. With subtraction, absolutely. So if you just want to get into a habit of doing it anyway, that won't hurt, all right? But the first thing I would ask right now is, do I need the parentheses? And you would say no, so you would drop them. So that's why I say if it helps you, yes, but at the end of the day with addition, you're going to drop them. So now I just try and collect like terms together. So I have a negative x squared. How about x's? They're gone. Plus 1. We're done. Now, something to consider. This is a new function, isn't it? It was created from two other functions. When you have two functions, you're going to put them together with addition, subtraction, multiplication, division. In any of the four cases, if someone asks you for the domain of this function, you do not look at this function. You look at the two it came from. Okay, that's very important. Your domain is based upon the two functions it started with, not what it ended up to be. Now, do we have any domain issues with either of these? No, right? No division by 0, no square root. So I move on. Part B, I'm going to do, no, not part B. I'm doing all the operations. I get to B in a second. Now subtraction. So yeah, this is where I would use parentheses. Bless you. So here's my f function. I'm going to subtract from it my g function. And now I cannot drop the parentheses on the g function. I have to pass the negative through first. So in doing so, I'd get what there? Minus 1 plus x, right? Now collect like terms. You have plus 2x in the middle now. So you've got that plus 2x appeared. Do we have any domain issues here? Is what? No? We're good? So I'm not going to write the domain, but it would be all real numbers here for both of these. Okay, how about for multiplication? So I write down fg of x like this. Now with multiplication, do I need to be considerate here of the parentheses around these or not? Should I? Absolutely, because if you have to multiply these two together, and they're both what we consider to be polynomials, right, powers of x, we'll have to FOIL this out, or expand it. So I'm going to just do my expansion here. You should get negative x squared, positive x cubed, plus x, minus x squared. Now collect like terms, and you're done. And notice that when I'm writing these answers, I'm putting them in, what's that called when you put it like this? Highest power of x and then down. They call this descending order. Highest power of x down. That's just the standard way of writing it. It's not incorrect to rearrange these. It's just not the standard way. All right. Mm-hmm. No, the leading coefficient is always the number in front of the highest power of x, regardless of where it appears in the, yeah. So it's always dictated by the highest power of x first. Yeah, if you put it in order, then it's always that number out front. Okay, now division. F over G. By the way, we didn't have any domain issues, did we? On that one? No? Okay. So if I take f, negative x squared plus x, and I divide it by g, which is 1 minus x, this is interesting. Because together, separately, did f and g have a domain problem? We said no, right? But when you do the division and you put f divided by g, do you have a domain problem? Yes, you do. You have an issue here. X cannot be 1. So you must throw that out. So what I was saying is you have to go back and look at the original functions. You have to consider that along with what you get. So it's like you're looking at all three. All right? What you get at the end you have to consider. What you started with you have to consider.
Consider that it doesn't have, it's not a function of, it's not a function. X is not a function.
Yeah. The name of this function is f over g. Yep, that's the name of it. It's kind of weird, but that's its name. Okay, so, hey, did y'all notice something here? Anybody notice that I could have factored out an x, and then you notice that these are the same things, exactly the same things, and they cancel? Which leaves you with just what? X. So is there a domain problem with this? No. However, you don't look at it after you simplify it algebraically. You look at it here. So I'm just showing you like the dangers here. You can start simplifying things and go, hey, I have no domain problem here. I have no domain problems with these. All real numbers. No, you cannot plug in 1. So I'm going to come back in here, and I'm going to say my domain for this problem. And at this point, I'm going to stop doing both notations, okay? I'm going to go with the one that's preferred, which is interval notation, all right? Negative infinity. What number could I not plug in? 1, union, 1 to infinity. Let's do a quick poll to make sure everyone's okay for everything I did on this. Yay or nay? Yes.
It is a function, but that's the domain. Even though it's not a function when x is 1.
A function can be a function. It just has domain restrictions. It's like the car wash can be the car wash. You just can't bring 18 wheels into it. That doesn't stop it from being a good car wash. This is a good function. You just can't plug 1 into it.
Answer coming out. You don't get 2.
That's right. It still follows being a function. Yes. 1 in, 1 out. Okay, let's move on to B. Any other questions? For B, I give you 2 new functions. I told you this is the first time I've taught this in many years, since they made it 1414. And they give the instructors, they're giving us like some guiding points, you know. And one of the big things is on the test, when you do arithmetic, it should involve functions that have square roots or that look like rational functions, like fractions. In other words, this first one is not going to be on a test. Something like this or like this is more like it. All right? Okay, so let's try and add these together first. All right, so when I add them, I just put a plus sign between them. Can you add those 2 radicals together? No. To add radicals together, they have to have the exact same radicands. What's underneath them has to be exactly the same. In this case, they are not. You cannot add them together. That is it. You are done. There's no more you can do to that. All right? Domain, though, we have to consider. And we have 2 domain issues here, don't we? We have, you can look at it up at the top or you can look at it here. We have to make sure that x plus 1 is bigger than or equal to 0. We have to make sure that x minus 1 is also bigger than or equal to 0. So I'm just going to jot that down. The radicand must be bigger than or equal to 0. The other radicand has to be bigger than or equal to 0. What type of things are these? What do we call these here? Inequalities. Are they quadratic inequalities like the one before? No, they are linear. Linear inequalities are easy to solve because you solve them just like linear equations. You isolate the variable x. So just subtract 1 on both sides here. X must be greater than or equal to -1. Over here, you add 1 to both sides. X must be greater than 1. Do not include? I don't know yet. I'm going to put these two pieces of information together. This is just solving the inequalities. Now let's draw a number line, and let's see what this looks like. Okay, here's -1. Here's +1. What is this first inequality telling me? My x must be greater than or equal to -1. So I can be -1, can't I? And then I must be to which side of it? To the right, how far? Forever. That's what that inequality says, right? Everything this way forever. Okay, what does the other inequality say? X must be greater than or equal to +1, which is everything from +1 to the right forever. Well, let me ask you, can I plug, according to this, the black here says everything to the right of -1, including -1. The red says everything from 1 to the right, including 1. What's our final answer? Everything from -1 on, or everything from 1 on? So what has to happen here, since this function is defined like this, you must be able to satisfy both at the same time. Both of them have to be satisfied. If you use something in the black over here, it'll satisfy one of them, but not both of them. If you pick something in the red, it's going to satisfy both the red and the black, won't it? So we only want everything from where on? From 1 on forever. So we're looking at what we call the intersection of the two sets. Question? Check 0. Plug 0 in, okay? 0's here, right? Okay, plug it in. 0 okay in here? 0 okay here? No. You see that? So it satisfied one but not the other. Everything to the one to the right will satisfy both. Does that clarify? Intersection of those two sets, yes. So our final answer is, in interval notation, domain is 1 to infinity. Include 1 or not? Yes. So that's it. Okay, what about subtraction? All you do is put a minus between them, right? That wouldn't change anything, would it? I mean, it changes the function because it's minus, but you can't put them together. Does the domain change? No. It's the same exact question you have to ask yourself, right? It's the same two radicands. So the domain of this one is also this domain that we had here, right? So that's going to work for this one and for this one. Now multiplication. When you take two functions and multiply them, you just put them next to each other. Now, what can we do here? Let me help you. I'll use this property. The square root of a times the square root of b is equal to the square root of a times b. In other words, you can put those two radicals together. And what's underneath them, like this is my a and this is my b, I multiply the two together. So this will become square root of x plus 1 times x minus 1, which is the square root of x squared minus 1. You cannot. Nope. Because there's subtraction between these, you cannot do like root of each one. You can't pull out the x because it's got a minus 1 there. You would have to have an x squared in both of these. Okay. So, domain. We already know this, right? We knew this from before, like the two functions separately. But what about this new function? How do we do a problem like this where we have a square root? We always look at the radicand, and we set up an inequality, right? X squared is, or minus 1 must be greater than or equal to 0. And how do we solve a quadratic inequality like I showed you in the problem earlier? First thing we do is we turn it into an equality, turn it into an equation. Can you all solve that equation? What are the two solutions? Plus or minus 1. I'm moving quickly, okay? Do I want to include plus or minus 1 here in my answers? The original problem had equality, right? So I want those. Then what did I tell you needed to do? Break it up into 3 pieces. Yes. And then do you know what this looks like if you were to graph it? It would be going up, right? Parabola going up. So it would still look like this thing right here. Yes? Like going down? No, no, because what's underneath these, they are not linear. I mean, they are not quadratic, they are linear, right? You don't have x squared. Here you have x squared, so you need to do something like this. No, wouldn't that be a problem? That would be a harder problem, and we address that later. Those are polynomial.
The domain is 1 on the functions together. You can have negative.
Well, let's see. Let's see what this is telling us, okay? If we look at this, right, then what is this telling us will work? Everything here, everything here, right? So what will our final answer be? What are you thinking? Man, we have so much to do. So the domain of, yes, you're saying the domain of this is everything from here to here and from everything here, here. However, because of the original definitions, right, of f and g, you have to take these two domains into consideration too. So what were these two domain restrictions? They gave us this, right? 1 and on forever. This one's saying you can have stuff in left of -1, but it's after our algebraic simplification that came into play. So we're still going to throw out this side, and it'll just be this on. I know that seems... What's that? Intersection.
They're still set. I mean, because we can't include the negative. I don't know. You said intersection is set for...
They overlapped each other, and so we said the intersection. Here they don't overlap. These two overlap, right? This one overlaps, well, I guess it overlaps with these two, so it's like 3 of them together. We will not include -1. Because that -1 will mess up, which one? This one right here. It'll mess up this function. You always have to consider where they started. When you put them together algebraically, you still have the restriction from where they started. There's something very subtle here, and I don't want to get us off track, but it's vital. How can I make this make sense more without killing more time? Imagine you're a company, okay, and this is like your payment function, right? X is the number of employees you have. This is how much your payroll is, okay? Then over here, let's say this is your payroll and X is number of people. Bonuses. Okay, fine, bonuses. Now, these two functions separately have restrictions on their domain. So if you want to add them together or subtract them or multiply them or divide them, you're going to create a new function. But whatever your original domain restrictions were have to follow you through that algebra. So if up here you're saying you can't have negative number of employees, at the end you can't say, oh, no, now it's okay to have a negative number of employees. You have to follow that through the algebra. Now, the difference, though, is if I just walk in here and I say, look, clean the slate, and I give you this function. Here we go. Brand new function, everyone. Here it is. What's the domain of this? Well, that one would be this right here, including the left side. Why? Because we don't know it came from two other functions, right? It wasn't defined that way. So that's a subtlety. Start with two functions, create a new function. Your domain is always going to be dictated by the two functions you started with. All right. How about this? Man, I'm always so optimistic that I'm going to get through this stuff quick, and it never happens. There's a fine line because, you know, if I go too fast, I lose everyone. If I go too slow, we don't finish enough material in this course, and that hurts you in the next class. Here we go. Oh, we never did division on that last one. Crap. We have to do division. It's OneNote. It's part of Microsoft Office. There's just a little insert thing here where you can add paper and take away paper. What was it? The F was the plus one. Okay, so I'm doing this over this, right? All right, there's our new function. You can put those together, but this is the most you can do. Bless you. Bless you again. Two roots in a fraction can become one root with a fraction inside. That's allowed. And now we have to determine, remember we have the original domain restriction, don't we? The original ones. And that said everything from 1 on to the right. But let's see if this changes anything. This is my radicand, isn't it? In radicands, we always set the radicand, what? Greater than or equal to 0, right? But you also have another issue at play here. What's your other issue at play? This denominator right here, right? X minus 1 cannot be 0, right? Because what happens if I let x minus 1 be 0? I get division by 0, right? I'm just going to put cannot be 0. So x cannot be 1. What did I say? I said x minus 1 cannot be 0. X minus 1 can never turn into 0, right? Which means x cannot be 1. So x cannot be 1, all right? It's no good to have x to be 1. And we need this to be true also. What type of inequality is this? We haven't dealt with this. It's called a rational inequality. So how do we solve rational inequalities? Well, the first thing you do is you try and figure out, and we'll do more of this later, all right? But for now, let's see if you can follow this. To figure out when this is going to be true, we turn it into an equality first. Isn't that what we did with the quadratic inequalities? We turned it into equality first. And now what I'm going to do is I'm going to multiply both sides of the equation by x minus 1. If I do that, what am I left with? X minus 1 over here will cancel. Over here, 0 times x minus 1 is 0. I'm doing this. I'm doing x minus 1 over here times x minus 1 over here. That's clearing my fractions. And now what does this say? X is negative 1. Hang tight. Well, look, what we're saying was for this to be greater than or equal to 0, we turn it into equal 0. We're saying to turn this into 0, we need to plug in negative 1. Does everyone agree with that? Plug negative 1 in, you're good to go. Yes? So what I'm doing is I'm drawing a number line. I know that I can have negative 1, right? That's a good number to have here. But I'm also aware that x cannot be what? 1? And just as before, this breaks our number line into 3 sections. But we run into a problem now. What's the problem? Well, I don't know what that looks like, right? The parabola was nice. Does anyone here know what this looks like? It's a rational function. It's weird. And we haven't graphed these yet, so I could understand why you'd be stuck here. But tell me if you can tell me what the final answer of this is going to be just from this information, without knowing anything about this right here. Greater than 1. Just greater than 1. We already knew to start the problem out, it had to be 1 or bigger, right? 1 or bigger. The only thing this gave us here is that x couldn't be 1. So my thought is I'm throwing out all of this because of the domain restriction I had to start off. Now it's just a question of, does that stuff work? Does this stuff out here work? So just someone pick me a number over here. 2? Plug 2 in here and see if it works. 3 over 1, square root of 3 is a number. That's fine. So anything to the right of 1 should work here. The key is not including 1 this time. Because negative 1 right here, wait, why doesn't negative 1 work? Because the original, remember where f and g came from. F and g, right, by themselves created this domain restriction. That said, everything from 1 on forever, including 1. When we combine them with division, we create this new thing, and it's saying it's got to be something like this. But we already knew from before it had to be 1 on. The only thing that we gain was that we throw the 1 out. I don't know, does that address the question? Let's take a poll. I'm pretty sure we're not going to reach 80, but it is what it is. We're going to have to stick with this one. This is like an A-level problem here. No, but it's not going to be possible to get a square root of negative. See, look, because we're saying from 1 on to forever. That's our final answer for this domain.
If x was 2, then it would be a square root of negative.
How do you figure?
2 minus, oh, I'm sorry.
Okay. At least it was one of those where it's just like, click. X greater than 1. X greater than 1. Oh, did we poll? Go ahead and poll while I bring up the next. Yeah. Whether or not you were okay with that last part. Jeez. You know. All right, let's try this last one, C. For C, let's do the addition. Actually, I'm going to do the subtraction, okay? Because the addition is almost the same as subtraction, except you don't have to worry. In the addition, you don't have to worry about this plus sign. And then what you do after that is the same as what I'm going to do here. Oh yeah, domain restrictions here. From the original problems, from the original functions, what were my domain restrictions? right here. X cannot be 0. That's it. If I plug 0 in here, division by 0. If I plug 0 in here, division by 0. So we know to start this off, X can't be 0. Right? Just to start. I'll write that up here on the side. X cannot be 0. All right. Now, if we're going to algebraically simplify these, I need to put these together. How do you put two fractions together? What do you need? Common denominator. I have an x squared and I have an x. So I'm going to create an x squared on this one, on the one on the right. To do that, I multiply that fraction on top and bottom by x. And that will give me x plus 1 over x squared minus x minus, well, you know what? Are you okay with me taking this x and distributing it through to the top there? Yes? I'm going to put parentheses around that and just show you I'm going to do this. So that gives me instead x cubed minus x over x squared. Now that you have the same denominator, you combine these two together. The one tricky part here is to consider what thing and not forget about it. The minus right here. That minus will distribute to each of those, right? And change those signs. Minus x cubed plus x. So we get x plus 1 minus x cubed plus x over x squared. And now clean it up. Negative x cubed plus 2x plus 1 all over x squared. That's it. I don't believe I can do anything else to that. Are there any domain restrictions here? X can't be 0, which was part of our original domain restriction anyway, so the domain is the same. All right? Addition would have worked exactly the same, except you wouldn't have distributed a negative. It just would have been plus, so this would have been plus x cubed and minus x. It's the only difference. All right, how about multiplication? Let's do multiplication on this one. Wish you were here. How do you multiply two fractions? What's that? How do you multiply two? That's if you're adding or subtracting. Just go straight across, multiply. Which means I want to just throw some parentheses around these and expand those or FOIL those. And on the bottom, straight across, x squared times x is x cubed. So x cubed on the bottom, that makes me happy. And on the top, x cubed minus x plus x squared minus 1. No, can't do that. This is it. Yeah, we're done. We cannot cancel these, right? Because this is not multiplication here. If you could factor an x cubed out of everything up there, then you could cancel. So this is it. What about domain restrictions? Still 0, so nothing's changed there. Last one, division. So I'm taking the x plus 1 over x squared. I'm dividing it by x squared minus 1 over x. Yes. That's what I want to do. I want to flip it and make it multiplication. However, let's just make sure we're comfortable. Everyone's okay with where that division bar is, where the longer one is, right? So flip and make it multiplication means x plus 1 over x squared times what? X over x squared minus 1. Now we have two fractions that we multiply, right? We multiply the top out. I'm going to multiply these two together, right? X squared plus x. Now this is all good, but What about some canceling? Couldn't I have canceled one of those x's? Yes? So hold on. Let's hold up on this for a second. I'm going to start canceling things, though. I got to be careful, don't I? What did we say about domains? You always look at the domain before the algebra. Right here, right now, let's talk domain. Right here, before we start canceling things out. X can't be 0, but that was the original issue, right? That's correct. This thing pops in here. This was never a problem before, but because of this division, that x squared minus 1 can never be 0, because then it creates division by 0. So you set that equal to 0 and you get positive and negative 1. You throw those out. So right now, here's what I know. X can't be 0, X can't be 1, X can't be negative 1. All three of those get thrown out. Now, I invite you to simplify, and let me help. Uh-oh, what'd I do? I recognize the x squared minus 1 is the difference of squares. And I did that because I noticed I had an x plus 1 up here, which I could cancel with. So here comes some cancellation. One of these x's is gone. All you're left with is 1 over x minus 1. What? Oh, yeah. Yes. How about I leave the x out there for now, and then on the next step, I'll put it in. Okay, yeah, so we had 1x here, and then the x minus 1. How is there a 1 if there's no? There's always a 1. It's like, no. Because it's like for the same reason, let me give you an example. If you have 4 over 4, right? What's that equal to? Well, you're canceling the 4. When you say cancel, what you really mean is this. You're reducing the fraction. You are dividing something into both numbers. So really what I'm doing when I'm canceling is I'm saying take 1/4, multiply here, 1/4, multiply here. Right? 1/4 times 4 is 1. 1/4 times 4 here is 1. So you're left with the 1 on top and a 1 on bottom. If I change this to a 4 over 8, I'm still multiplying by 1/4, 1/4, right? On the bottom, what do I get? What's 1/4 of 8? That's going to be 2, okay? But what's on top still? 1. See, 1/4 times 1 still leaves you with that 1. And that's exactly what's happening when you cancel there. You're actually multiplying by 1 over x times 1 over x across top and bottom, and then you're left with the 1 up there, okay? All right, we are done. What's the domain here? Everything except 0, 1, and negative 1. Let's do it in interval notation. Everything negative infinity all the way up to negative 1. I don't want negative 1. Jump over it. Everything from negative 1 to where? 0. Don't want it. Jump over it. Everything from 0 to 1. Don't want it. Jump over it. See, this is one of those problems where interval notation kind of sucks. You're saying everything all the way till you get up to negative 1. Whoop, jump over negative 1. All the way till you get to 0, jump over 0. All the way you get to 1, jump over 1. All the way from 1 on. It's mainly used in math from here on. So that's why very seldom will we see set notation in calculus. It's usually interval notation. It varies. I mean, it really...
But you could do, could you just say, like,
the set of x such that x is... Yes. I'm just saying I'm doing interval from now on. I don't care how hard it is. I'm going to do it because I want you to see... I mean, that took me maybe 5-6 seconds. You know, I mean, it's not like... If I understand what I'm doing, it's not a deal breaker to do it in interval notation. Okay. God, we're still in 3. We're supposed to get through 3 today. All right. This is a very important topic. All right? Very important. And How many of you, just by show of hands, have heard of the difference quotient? I know some of you have taken this class, so you've heard of the difference quotient before. All right? Or no, vote. Let's vote on your clicker. Have you heard of the difference quotient? Yes or no? Sort of, okay, if it's sort of. Okay, so that looks like we've got... There's more than what? What's going on with the responses? Why? Let's start over. Difference quotient, yes or no? Are y'all allowed to vote more than once?
You can push more than you can change your vote.
Yeah.
If you push like 3 and up, then it makes
No. I need to fix that.
We don't have 3. Oh, how do you know?
Yeah, you don't. Yeah, you don't. I added this later.
Oh, okay.
Wait, no, hold on. Is that the one you picked up over there? One of the packets you picked up today, the packet you picked up over here is a continuation that these notes weren't there last time. So you've got this stuff. Yeah, I don't know. We're getting 35 responses. This is not good. All right, who cares? Let's just keep going. Okay, so a lot of you have probably heard of the difference quotient. Well, some of you have heard of the difference quotient. Super important. I'm going to try and give you a geometric look at it first, just to let you know like why we're doing it, all right? It's used in calculus. So here's what it is. All the difference quotient is a fraction that you create from a function. You take the function, you plug in x plus h, you subtract from that just the function itself, you divide it by h, and that we call the difference quotient. And a lot of times students are like, well, why the hell do you even care about difference quotient? So let's look at this. We're going to study this more later. But remember from some point in your life learning about slopes of lines. Do y'all remember ever hearing about the slope of a line? Slope of a line, they always said was what? Rise over run? Okay. So slope, we always called it m, was rise over run. It was the change in your y divided by the change in your x. But in order to find the slope of a line, you had to have 2 points, didn't you? x1, y1, x2, y2, then you do rise over run. All right, so here's a graph, all right? I am going to label a point on this graph. I'm going to pick an x value. And the x value I'm going to pick is x. I'm not going to tell you what it is. Then wouldn't you agree that the y value here is how high it is? And that's whatever f of x is. When I plug x in, whatever the function spits out, that's how high it is. Everyone with me? Okay, now I'm going to pick a second point. That second point isn't going to be x. It's going to be x plus a little bit. How much? How about h? I'm not going to tell you what h is, but it's x plus something. Understand? Here it is. There's the point, x plus h to here. Does everyone understand that the distance between these two is h? So like if the first one was 2, the next one was 2 plus 1, then the difference would be 1. So it's whatever the h is how much more I'm adding. If I change the h, right, that point changes, doesn't it? If I move that around. What we are interested in is figuring out the slope of the line connecting these 2 points. We want the slope of that line, which is rise over run, right? Which is the y-coordinate of the second point minus the y-coordinate of the first point. Well, what was the y-coordinate of this blue point? Well, it's the function at that value, right? F of x plus h. What's the y-coordinate on the first point? F of x. So the rise part of this formula would be f of x plus h minus f of x. That's y2 minus y1. Let's vote. Yes or no? Do you understand that? Because if you don't understand, it's not even worth talking about. The rise is f of x plus h minus f of x. And then the run we said was how far? What's this distance? It's h. It's the x2, which is this one, minus x1. So if you take x plus h and subtract x, you get h. So do you see that this quotient right here, this thing we call the difference quotient, gives you the slope of the line connecting 2 points on a curve. Yes? In calculus, what we want it to do is this. We want to try and talk about the slope of a line at 1 point. What's wrong with that? We define slope by 2 points, right? So watch this. Watch what we're going to do in calculus. I'm going to try and, in calculus, I'm going to want to know what the slope of the line at this point is. Do you think that that's the slope at that black point? No, that doesn't look like the slope there, right? So watch what happens as I bring that blue point closer and closer. Is that getting better as an approximation? Now I'm going to zoom in on this. Okay. So now I'm bringing it closer and closer. Do you agree that I can get closer and closer and closer and closer and closer? And we've talked about this, closeness, right? How close can you get? As close as you want to get, right? So I mean, this slope of this line is defined. If I get a little closer, it changes a little bit, right? If I get a little closer, it changes a little bit more. But it's approaching a certain, I mean, would we all agree it's getting really close? That line is getting really close to something. Yes? Like when I get there, what happens? When I actually put that other point on top of the other point, what happens? That formula breaks down, doesn't it? It becomes division by 0. Calculus gets around that. All right? We are able to get around that. And so what we can do in calculus, we can define the slope of this line at 1 point only. But to do it, we in calculus must be able to compute a difference quotient. The algebra we have to be able to do. Once we do the algebra, then we use a little bit of calculus to finish off the problem. All right? And if well, it is, but when you get close to it, it's headed to one place only, right? I agree that if I zoom back out, you would say, hey, you know, look, that is not close enough, okay? Because this slope of this line is way off from what the slope of that line is. But as I get closer and closer, it is approaching one value. I hope that makes sense. Okay? Now, as evidence, this is my lecture notes from my last calculus class. And a lot of what I'm doing here in these problems, no, that's not it. Here's an example. Look at this right here. That right there is a difference quotient. So in this class, we look at it and we start doing stuff to it, and at the end we do a little bit of calculus. We do this thing out here, which we're not going to talk about in this class. All right? But you see that in the calculus class, I must be able to set up the difference quotient. This is our f of x plus h minus f of x over h. That's it right there. Okay, I hope that somewhat sells you a little bit on the idea that you're going to need it later and that maybe it has some value. Yes, this is absolutely one of the most important sections on the test, is being able to do difference quotient. Where are my notes? There we go. I'm sorry? Oh, no, it's not. I'm just trying to give you a visual representation. Do we have any computer science majors in here? Computer science? Okay. I'm not a computer science major. I am a math person. But when I was in math, taking math courses, I had to learn how to code. This is the code that I wrote to make this happen. Okay? So if any of you that are computer science majors are interested in my code, I give this stuff away free if you want. I just have to be able to give you, like on a jump drive. I code in C++. This is C++, and it's part of Mathematica. That's the program I'm using. But everything I'm showing you up here, all these little sliders and all this stuff, was created by me so that I could try and visually help you understand what the hell we're doing in here. All right? Okay. So, with the knowledge of the difference quotient, everyone needs to memorize this, okay? The difference quotient needs to be memorized. It's one of those things. It's on your formulas, all right? It's on the notes I just gave you. That's your difference quotient. Sorry, this marker sucks. F of x plus h minus f of x over h. That's the difference quotient. Anybody, you give me any function, I don't care what it is, I can always set up a difference quotient. So I've written down 4 different functions. We're going to find and simplify the difference quotient for each one of these. And they're going to get progressively harder and harder. All right? How realistic was it that I was going to get through this today? Unbelievable. All right, so part A. My function is negative 2x squared minus x plus 3. Let me turn the light back on. So the difference quotient is made up of 3 components. Look at it as the top left, the top right, and the bottom, right? The bottom will never change. It's always going to be h. The top right is f of x, which will always be given to you. So the only thing that you really have to figure out is this f of x plus h. And this goes back to when we were evaluating functions back a couple of sections ago. Was it 3.1? Early in 3.1? Are we still in 3.1? Holy shit. Hold on. Yeah, this was earlier this section, wasn't it? Yeah, right here. In 3.1.5, evaluating functions. Do you remember me telling you that this was going to be important? This is why. You have to be able to plug x plus h into a function. Got to be able to do that, because it's the top left corner of the difference quotient. Okay? So, since that top left is so important, I'm going to just spend some time real quick writing it down. I plug 2 plus h in, so how is this going to look? Negative 2, x plus h squared minus x plus h plus 3. What are things that I see students do that are incorrect? Minus 2x squared plus h minus x plus h plus 3. They leave this alone. They say, oh, but I'm supposed to add h, so they just add an h in there. Or they put this x and they put an h there. Or I'll see students do this, negative 2x squared minus x plus 3. Oh, but wait, I'm supposed to add h. So they add an h at the very end. These are all incorrect. The only correct way to do it is to replace every x with x plus h, right? Okay. Now, algebraically simplify that. That means multiply it all out if you can. See if you can do that. So negative 2 squared plus xh plus h squared minus x minus h plus 3. So I just expanded out x plus h squared first, distributed a negative through here, plus 3 here. Now I'm going to come through with a negative 2. Oh, I forgot my 2. Yes, thank you. Negative on my sheets. I need to slow down. I'm rushing. I just need to concede that we're not going to get through 3.3 today. Okay, I'm okay with it now. All right. Any questions? We haven't even done the difference quotient, have we? Okay, that was just the f of x plus h. That's always the first difficulty in the problem. Now, difference quotient time. F of x plus h minus f of x all over h. This is now equal for me. The top left is everything I just wrote down up here. Right? That's the top left. Okay, so let's put it there. Now, the very, very important next step is to recognize and remember that now you're going to subtract, right? You're going to subtract what? F of x. And f of x, in our case, is a bunch of stuff, isn't it? So what should I put here? Parentheses. What if I forget them? It's over. At that point, it's over, okay? You cannot forget the parentheses because that negative's got to pass through all the terms. So now let's write down f of x and then all of that divided by what? H. So the yellow here, that was our f of x plus h. The part over here, what was that pinkish stuff there? That was f of x, right? Got our minus sign, right? Minus, don't forget that. Parentheses. And now let's just put everything together. That means I have to distribute that negative through, right? So I get negative 2x squared minus 4xh minus 2h squared minus x minus h plus 3. Then what? Plus 2x squared plus x minus 3 all over h. Now the question you're going to ask is, when am I done? You are done when this h down here isn't down here anymore, which means you have to be able to get an h out of the top and cancel it. That is the hardest part of the calculus part when you get to it, is all of this part. Okay? So we have to be able to get an h to come out. If we cannot get an h to come out, we messed up or we're not done. But some good things should happen. If you do all this properly, good things should happen. Do you all see it? Negative 2x squared, positive 2x squared. Cancel. What else cancels? X's cancel. And the 3 and the negative 3 cancel. And what are you left with when all that stuff goes away? Negative 4xh minus 2h squared minus h all over h. Notice anything in the numerator? Every one of them has an h, so you can factor an h out. You could, but since there's an h down here, I'm going to just pull an h. You could, but when you cancel, just remember it would become a negative 1 when you cancel it. All you're doing is removing one factor of h from each of the terms. Don't forget that's a negative 1 at the end, because you pulled that h off here, which left something there, right? Now the h's cancel. And now just write down whatever's left. Negative 4x minus 2h minus 1. Box it up. Well, no. You should be able to cancel that h out. I mean, is there ever, in this class, no. Later on in calculus, there will be things that happen where we'll have to approach it a different way. We can't get the h to cancel, but we'll do something else. You could change the order of this any way you want. Okay? So, let's just recap. Most important first step, figure out what f of x plus h is, right? Just figure it out, write it down, figure out what that is. After you figure it out, you plug it into the formula, right? Remembering the minus sign distributes. Put things together, and then not hope, but you have to force what to then happen. Get the h to cancel, all right? So getting all the way to, let's say, this step in canceling right here and just leaving it like this, you're not done. You've got to get to here. Let's try another one. New function. The function is 1 over x cubed. So I'll start out by figuring out what f of x plus h is. So is it this? No? Anybody want to volunteer to do it that way on a test? Anyone want to volunteer to do it like that? Okay, don't. All right? Don't volunteer to do it that way. It has to be in parentheses, right? The x plus h has to be in parentheses. So it should be instead that, right? Oh my goodness. Do y'all see how that's going to become not good? Like that's going to be kind of ugly? All right, if this right here is going to turn out to be ugly, if it is, the previous problem, it wasn't too bad, right? I mean, we figured it out, it was all right. This one looks a little bit kind of ugly. So what I'm going to do is before I go try and figure all that out, I'm just going to set up the difference quotient, take a look at it. See what I've got, okay? Is that all right with you? Here we go. Difference quotient, DQ. It is f of x plus h minus f of x all over h, which for us in this problem is 1 over x plus h cubed minus the top right corner, which is f of x. What's f of x? 1 over x cubed, right? Just 1 over x cubed. We done with the top? Is that this right here? Yes? All over then h. And now you look at that and you go, wow, okay. How am I ever going to get an h to cancel here? It's trapped inside here. It's in a denominator. Yes. Down here? Say again? I'm not understanding. Over here? Like this? And get rid of this? But yes, but you still then have h on the bottom. It doesn't look like it, but that's the same thing, right? You never got it to cancel. You've got to get it to cancel. Can't just move it where it looks like it's somewhere else, but it really is down there. Yeah. Yes.
Where do you get the 1 over x?
Okay, so this right here is f of x. This right here is f of x plus h. Then you have the minus sign between them. Yes. Yeah. So yeah, the difference quotient doesn't care where your function comes from. But the only way I can ask for a difference quotient is if I give you a function, right? If I don't give you a function, I say, give me the difference quotient. That's what you give me. I give you a function, there you go. Now the difference quotient is something you can compute. All right. Any ideas? Sometimes you just have to see it. I'm going to get a common denominator between these. Why? Well, that's what we did when we had complex fractions, right? We got common denominators. So let me see. The common denominator, what would I need to introduce on the top and bottom on this one? X cubed. X cubed up here, x cubed down here. What would I need to introduce on top and bottom here? X plus h cubed over x plus h cubed. Now rewrite the entire thing. That I wasn't going to say that? Have I told you all that my opinion of calculus is that it's algebra on steroids? Have I told you all that? No, I haven't said that. That's what I always say to my calculus students. Calculus 1 is algebra on steroids. But hopefully a course like this, you're getting pumped up a little bit, first, I don't know, so to speak. The problem in the past algebra classes, you weren't doing enough of this. And so you get to calculus and you're just way too deficient. Students were way too deficient. So this sort of algebra, although it's bad, is what you're going to deal with in calculus. So we want to start getting our hands dirty now. All right, so do I have a common denominator? Okay, so put them together. When you put them together, you combine the numerator, this minus this, right? All over the common denominator. So I'm rewriting things. When your hand starts to hurt is when you know you're starting to actually do some math. So I've combined them. Can you do anything up here? How about x plus h? Why don't we cube it? Why would I do that? So let me think about this. Remember what we talked about with Pascal's triangle? Did we do that thing? No, it wasn't in our notes? Okay, I believe you. Don't worry about it. I'm not going to get into it right now. All right, now here, let me see if you believe this. If this was x plus h squared, if it was, what would be the first piece we would get? X squared, right? But since it's x plus h cubed, what do you think the first thing that we get would be? X cubed, and look what we have out here. X cubed, and then we'll be taking away that x cubed, which means they're going to cancel, right? And everything else is probably going to have an h in it. What do you mean, bring it out? I want to multiply the whole thing out. I do. I want to figure out what x plus h times x plus h times x plus h is. That's what I'm going to do. I'm going to do it as scratch work right here. I'm just going to stop. I'm going to say, what's x plus h times x plus h times x plus h? And then after some time and effort, you would determine that it is, oops. Didn't you have a quiz over this? One of your first quizzes was like this? Where you had to multiply something out 3 times like that? Except it had numbers. Now it's just all letters. So I'm going to leave this as an exercise for you. Make sure you can do that. I would start by multiplying these two together. Once you figure out what that is, then distribute the x plus h through. Clean it all up. You should get this. Okay? So let me go back up to my difference quotient. I have that x cubed right there in the top left. I'm going to subtract all of this, right? Subtract all of this. Do you want me to change the signs now, or do you want me to put it all in parentheses and then do another line where I distribute? Change signs now? Okay, don't forget, on your quiz or test, do not forget. I'm going to hold you accountable for that. Yeah, I can't unlock the door. It's one of those ones that I can't control that. Okay, is this what the top would become? Got your x cubed. You're taking away every term from this, which should turn into that. What do I still have below this? That's further down. I still have the common denominator, don't I? Just leave it. We don't ever touch these denominators unless we absolutely have to. Okay, something good is about to happen. My x cubes are going to cancel. And when that happens, notice everything up here has what in it? H, H, and H. They all have an H. And that means I'll be able to factor an H out, which is what I'm going to do on the next line. So on the very top, I pull that H out. I'll have a negative 3x squared. I'll have a minus 3 xh. I'll have a minus h squared. And this will all be over the common denominator, x cubed, x plus h cubed, and this is all over h. And remember, h is like h over 1, right? So what I'm getting at is that I could flip this fraction up, or if you're comfortable, you just cancel those h's out. Whichever way you feel more comfortable. And at that point, you're done. Now, I would rewrite it one more time, this whole thing, without the parentheses around it, so that I would get something like this. Negative 3x squared minus 3xh minus h squared all over x cubed, x plus h cubed. That's what? Okay. I'll look at it. Questions? What's that? Remember now, we talked about building a house, right? We talked about tools, and we talked about learning how to do a hammer and everything else, right? I did mention that? You got to keep this all in perspective. Can't build anything unless you can do algebra. Once you can do algebra, you can build stuff. So, you know, how would I use this? It would depend. You know, you're faced with a problem in the real world. You have to come up with a way of attacking it. And a lot of times, it's going to break down to algebra. Now, I was trying to show you with that thing, that line, that what this allows us to do is find the slope of this tangent line, right? Well, why would that be important? Well, how about this? When you talk about, let's talk about speed, all right? Like velocity. Are you comfortable with the idea that speed, you look down at your speedometer, driving to work or driving to school, right? And look down, it says 105 miles per hour, right? So what does that mean? 105 miles per 1 hour. Now, does that mean that if I get pulled over, the cop says, you were doing 105 miles per hour, say, hey, I've only been on the road for 5 minutes. How could I go 105 miles in an hour? You know what I'm saying? Speed always requires two things. A distance you travel, right? You have to travel some distance. In this case, 105 miles divided by some increment of time, in this case, per hour. So how can a police officer ever tell me that my speed at a specific point in time was that? It's an average. So going back to my picture, this is like the starting point, okay? Time is the x-axis and distance is the y-axis. So if I actually travel a certain distance over a certain amount of time, then the slope of this line represents my average speed for the trip. But is it possible to talk about the speed at an instant in time? The answer is yes. The way to do it is with calculus. The way to do that requires the difference quotient. The way to do that requires algebra. Now, why would you want to talk about the instantaneous speed of something? Because what if I'm creating an engine and I've got a piston, right? I've got a crankshaft that's spinning at a certain speed, and then I've got a piston that's somehow moving in relationship to that crankshaft, right? And I want to know at a certain instant in time, at that instant right there, the rate at which that corner of the piston's moving, okay? The relationship to how fast this is turning. We're talking about instantaneous speeds, instantaneous rates of changes of things. You're filling up a container, right? Let's say you're filling up a funnel with beer, right? You like that. So it's a beer funnel. You're filling it up, right? And you're just holding it, pouring it at a constant rate. What happens is that initially it comes up very fast, right? If it's like a cone, it comes up really fast, and then it starts to slow down. Why? Because it's spreading out, right? The cone's spreading out. So maybe you want to know at an instant in time how fast it's coming up. Now, that's a beer bong. Who cares about that? What if it's a river? What if it's a lake that's about to crest? I mean, in mathematics, we want to know what's happening at instance. Okay, finding stuff over average times is easy. It's always been easy. It's the instantaneous stuff that really matters when it comes down to physics and chemistry and chemical reactions. What's happening right then, and the calculus allows us to talk about that. I don't know if that helps, but that's okay. All right. You have to believe me. You don't put men on the moon without calculus. You don't do that. Okay. And you don't have your phones without calculus. I mean, everything we have requires mathematics. It has it in there, right? All right, well, I'm out of time. So here's what we're going to do. You see this one right here? 1 over x minus 2. And this one right here? I want those to be quiz problems. Okay? Now, the way I'm going to treat it is this. I want it to be turned in as a quiz grade, but I want to see effort. I'm not necessarily going to grade a correct answer as much as I'm going to see that you tried the algebra, all right? That you tried the algebra involved in these. And also try and get started on the homework for this section, all right? Finish up the rest of the homework. B and C. To be turned in next class, at the beginning of class, you're C and D, sorry. C and D. If you run into problems, get with one of your neighbors, go to the tutoring lab, see if they can help you. Do your best. Yes, but again, don't focus so much about, I've got to get the right answer, so I'm just going to find someone who knows how to do it. I want you to try and play with the algebra. You know that an H needs to cancel, right? Yeah. Okay. Read the book also. It has some helpful hints. Let me turn off my recording, and I'll be right with you, okay?